let us discuss about the magnetic effects of electric current. What is the meaning? It means that when electric current is passed through a conductor, then that electric current is capable of producing magnetic effects around it, around the conductor. How can we say that? Very good. Now, if we have a current carrying conductor and if I place a compass close to it, then it is observed that there is deflection in the magnetic compass. Now, the question arises, why there is a deflection in the magnetic compass? This means that the current which is flowing in the conductor is definitely producing some magnetic effect, some magnetic field, due to which the needle or the compass needle is deflecting. So, what we conclude? That the electric current which is flowing through the conductor is capable of producing magnetic effects. Now, if we stop the current, then there is no deflection in the magnetic compass. This means whenever there is a current in a conductor, there is a magnetic field associated with it. That is the magnetic effect. So, this is one part of magnetic effects of electric current, that is magnetic field. Now, the question arises, how to find the direction of this magnetic field? The direction of the magnetic field is given by the right hand thumb rule. Right hand thumb rule means what does it state? It states that visualize the current carrying conductor you are holding in the right hand in such a way that the thumb points in the direction of the current. Then the curl of the right hand fingers represent the direction of the magnetic field around that conductor. Means, suppose this is a current carrying conductor and the current is flowing from this end to this end. So, first of all, point the thumb in the direction, then the curl in the finger represents the direction of magnetic field this way. Now, if this is the current carrying conductor vertical, then the thumb represents the direction of magnetic field, electric current, then the curl in the finger represents the direction of magnetic field. So, here we have a very important observation. If the current is in the vertical direction, the magnetic field is in the horizontal plane. Second thing, they are concentric circular rings. Now, it is clockwise or anti-clockwise depends on the direction of current. If you take current moving in a direction vertically upwards, then the curl in the fingers, you see, it is showing you anti-clockwise. Now, reverse the direction of current. Current is going down. The current is going down, the curl in the fingers, they come to be in clockwise direction. That is exactly how we can represent the direction of magnetic field. One more way by which we can represent is by the dots and crosses. If the magnetic field is perpendicular to the plane of the paper, now if I represent it by dot, this means it is coming out of the plane of the paper. And if I represent it by a cross, that is, it is going perpendicular to the plane of the paper. That is one way by which the magnetic fields are represented as well. Now, what happens if a charge is released in that magnetic field? So, this is what we are taking now, charge released in a magnetic field. So, magnetic field is already existing in that region and we are releasing a charge. Then what will happen to the charge? First thing that comes to our mind is the magnetic field can exert a force on the charge. So, let us try to find out. Now, here the first case that I am taking is case 1. The charge is released at an angle theta is 0 degree. Now here let us see how exactly this is happening. Suppose that the magnetic field is horizontal this way, uniform magnetic field. How can we say that is a uniform magnetic field? A good question. See, the magnetic field lines are parallel to each other, they are evenly spaced. So we can say that the magnetic field is uniform. Let us say this is represented by a B vector. Now what we say is the charge is released at theta is 0 degree, which means that a charge q is released with a velocity v such that it is in the direction of the magnetic field. In such a situation where a charge is released parallel, in such a situation it is observed that the charge moves undeflected and undeviated as well. So if we say that the charge moves undeflected, undeviated, what is the conclusion? This means that F is 0. That is, the magnetic field is not exerting any force on the charge. The charge is not experiencing any force due to the magnetic field. So this is what we observe, that if the motion of the charged particle is parallel to the field direction, then there is no force on it. So motion will be, motion of charged particle is straight line. This is what we can say, straight line. Now second case we take, let us say case 2. This is where we say that the charged particle is released at 90 degree. 90 degree to what? To the direction of the magnetic field. So how exactly? Let us see it in the diagrammatic form. Let us say this is the direction of magnetic field in a region, uniform magnetic field, a charge q. Charge q is released perpendicular to the direction of magnetic field. So this is how the charge is released. Now when the charge is released perpendicular to the magnetic field, it is observed that the force because of the magnetic field is directly proportional to the amount of charge carried by it. It is also directly proportional to the speed with which it is released. So combining these two, we can say F is proportional to Q into V. Therefore F is equal to a constant of proportionality B Q V. So this is the maximum force that the charge can experience. So since it is released perpendicular to the magnetic field, so we can say F, this is B Q V. Now this is the force, so this is the magnitude. This gives the magnitude of the force. You can say this is magnetic force because this is the force experienced by a charged particle due to the magnetic field. Now what is the direction? The direction of the force is given by Fleming's left hand rule. Now what is that? It states that stretch the 3 fingers of your left hand such that they are mutually perpendicular to each other. That is exactly how we can go to stretch. Then the first finger represents the direction of the magnetic field. Then the middle finger represents the direction of motion of the charged particle. Then the thumb represents the direction of the force. So, that is exactly how, by using Fleming's left hand rule. Fleming's left hand rule, this gives us the direction of force. That is exactly how the magnitude and direction can be found out. Now, the question arises, what is the path taken by it? Yes. Now, see, if we say that a charged particle is having motion this way, and the magnetic field in that region is inside the plane of the paper. So, magnetic field is inside. So, let us use the Fleming's left hand rule. Magnetic field is inside, it is moving this way. So, the force appears to act in this direction. This is the direction of the force, because B is inside. Now, let us take one more point. Let us say this point. If I take this point, now V is, say, in the upward direction. This is the direction of B. B is already perpendicular to it. Then what we find? The force is in this direction. Observe carefully. Again, let us take one experimental point, third point, where the velocity is in this direction. B is vertical inside. Say, what we find? Force is this way. Now, observe carefully all these three cases. We find that the forces appear to act towards some point, which means that this force is behaving like a centripetal force. Now, when centripetal force acts on a body, then the body continues to move in a circular path. Therefore, in this case, we can say that the charge is moving in a circular path. So, what is the path taken by charged particle? This is circular, very important. This will be extensively used in numericals. So, when a charged particle is released perpendicular to the direction of magnetic field, then it moves in a circular path. Now, when it moves in a circular path, then the question arises, what is the radius of that path? Very good. So, now the magnetic force is providing the centripetal force. Therefore, magnetic force is BQV and centripetal force is mv square by r. So, from this we can say r is equal to mv by bq. Very important expression, extensively used in the numericals. So, we get r is equal to mv by bq. What can we conclude from this? This means r is directly proportional to mv, and that is momentum. So, radius of the path taken is directly proportional to the momentum of that charged particle. Secondly, we can say r is m by q. This also we can say, that is, or inversely proportional to q by m ratio of the charged particle. That is exactly how we can conclude from the given expression, very important. Now, if it is moving in a circular path, then definitely it will take some fixed time to complete that circular path. So, that is called time period. Let us try to find that. So, time period. Time period will be distance, which is 2 pi r, by speed, which is velocity. So, this gives us 2 pi r by v. Now, 2 pi. Now, we know that r is equal to mv by bq. So, we want r by v. So, m by bq. So, 2 pi m by bq. This is the time period of that charged particle in the magnetic field. Also, I can say 2 pi by t is bq by m. In other words, angular velocity omega is bq by m, which means that both the time period and the angular velocity are independent of the radius of the path. Very important conclusion. This frequency is also sometimes known as cyclotron frequency. So, all these analysis that we did, let us draw some conclusions based on it. The first conclusion that we draw is, when a charged particle is released perpendicular to the magnetic field lines, then it moves in a circular path. The second point that we can say is, the radius of the circular path is directly proportional to the momentum of the charged particle. Then the third important conclusion is, the time period as well as the angular velocity of the charged particle is independent of the radius of the path. And one more thing, the direction of the force and the displacement, they are perpendicular to each other, because this force is behaving like a centripetal force, and the centripetal force always acts radial, and the displacement is, if you see, draw tangent to the circular path. So, they are perpendicular to each other, which means that no work is being done by the magnetic force. So, if no work is done by the magnetic force, then by using the work energy theorem, what we can say is, change in the kinetic energy is 0. Very important conclusion. The magnetic field cannot change the kinetic energy of the charged particle, which means that the speed is going to remain constant. Velocity changes because at every point tangent to the path, direction of motion changes. So, velocity is changing, what we say, but the kinetic energy is going to remain the constant. The magnetic field is not capable of changing the kinetic energy of the charged particle. This is a very important point of distinction between electric field and magnetic field. Electric field, a charged particle accelerates in the electric field, that is why we say F is Q into E. But in a magnetic field, the magnetic field cannot change the kinetic energy of the charged particle, while in an electric field, the charge experiences a force F is QE in the direction, if it is a positive charge, in the direction of electric field. Since it is accelerating, its velocity is increasing, speed is increasing, kinetic energy is increasing, but that does not happen in a magnetic field. The fact that the radius depends on momentum is utilized in constructing mass spectrographs, and the fact that angular velocity is independent of the radius, it is used in constructing cyclotrons. Now, let us go to the third case, which could be that we have seen when the charged particle is released parallel to the direction, in the direction of the magnetic field, the charged particle moves along the straight line path, undeflected, undeviated. When the charged particle is released perpendicular to the magnetic field, we have seen it is in circular path. What if the charged particle is released at an angle which is between these two, 0 degree, and it is between 0 and 90. Now, how exactly? Diagrammatically, if we see this, it is something like this: magnetic field, uniform magnetic field. This is the uniform magnetic field, let us say B. Now, a charged particle is released at a velocity v, which makes an angle theta with the field direction. This is exactly what the situation. Now, what we can do here is the direction of the velocity, we can resolve it as v cos theta and v sin theta. Observe, v cos theta is in the direction of magnetic field. Then what will happen? Because of v cos theta, the charged particle will move undeflected, undeviated along the straight line path. Because of v sin theta, since v sin theta is perpendicular to the magnetic field line, the charged particle will have a tendency to move in a circular path, which means that the direction of motion taken by the charged particle is resultant of these two effects. So, what could be that? That is exactly what happens is the charged particle will try to move in a helical path, like this it will move. Why is it moving this way? The reason is because of v cos theta, it will have straight path, straight line. And because of v sin theta, circular. So, if we combine these two, then the charged particle will not be able to move in a complete circular path. The moment it tries to complete the circular path, it will experience a force, or it will have v cos theta, which is trying to push it. Again it will try to move in a circular path. Again when it tries to complete, retrace it, it again gets pushed v cos theta. This means that it is not able to retrace its path in the circular fashion. So, what happens is it has a motion which is in the form of a helical spring, this path. Now, this is called helix. So, the path taken in this case, therefore, we can say path taken is helical or helix. If it is between, if the velocity is between 0 and 90. Now, what will be the pitch? Pitch of the helix. What is the meaning of pitch? Pitch is horizontal distance between two consecutive circular path. That is, this is one center, this is another center. So, this distance is called pitch. This is exactly what. So, therefore, what we can say, pitch is d. Let us say this is horizontal distance. How will you find horizontal distance? Horizontal distance is nothing but horizontal velocity into time. Horizontal velocity is v cos theta and time is 2 pi m by b q. This is what we can say. So, what we have now? This is 2 pi m v cos theta by b q. This is the pitch. Now, what will be the force? So, force F will be B Q, but V will be what? V sin theta. So, therefore, F is equal to B Q V sin theta. Now, this can also be written as F vector is Q V cross B, because sin theta occurs in cross product. That is exactly how we can write in general. This is the general expression for the force because of the magnetic field on a charged particle. Now, if we say that if theta is the angle between, this theta is angle between the velocity vector and the field vector. In easy way, it is the angle between the direction of motion and the direction of the magnetic field lines. Now, see, if the equation is very general. See, if we see that the charged particle is released parallel to the magnetic field, theta is 0, sin 0 is 0, so we get force is 0. And if it is perpendicular, sin theta, sin 90, 1, so we get this. That is exactly how we can get the expression, general expression F is equal to Q into V cross B. Let us now take an effect where we have motion of a charged particle. Here I have considered an electron under the combined influence of electric and magnetic fields. First, let us analyze individual and then we will take the combined effect. First, I am taking effect of electric field. See, ABCD is the region where electric field is there. Let us say the length is small l. A charged particle Q is released with a velocity v in this direction. This is an electron, so this Q should be E. Now, the electron will be attracted toward the positive plate. Okay. So, observe the electron gradually deviates from its path, and when it comes outside the region ABCD, it starts moving in a straight line path. It strikes at S on the screen placed. So, we have to analyze this situation, what is the nature of the path taken by it. Now, the direction of electric field is mentioned here from positive plate to the negative plate. Now, what we can say is F is equal to Q into E. This is what we can say. Now, but F we can say m into A, because when a charged particle is released in an electric field, it is accelerated. So, that is an accelerating force. Therefore, we can say m into A is equal to Q into E. From this we can say that the acceleration is, this Q is E by m. This is what we can say, this is the acceleration with which it goes. Now, the force is in vertical direction and the charge is released, the electron is released in horizontal direction. So, by using S is ut plus half at square along vertical direction, what we get? Y is equal to vertical displacement. Let us say y is, since it is released in the vertical direction, charge is released horizontally. So, I will write here Sy uy into t plus half ay into t square. So, passing on all the values that we know, y, uy is 0 because the charge is released horizontally. So, vertical component will be 0 plus half a E by m into t square. So, we get an equation y is equal to half of now we can say, but t is what? X by v, you are releasing with a velocity v. So, distance travelled, let us say, is a Therefore, we get y is equal to half of from this what we conclude, half very important conclusion, y is proportional to x square. This implies the charge, the electron will move in a parabolic path, that is to say inside the electric field, that is in the region ABCD, the charge particle will move in a parabolic path. That is exactly how we can confirm. Now, when it comes outside, this was the deflection that we saw equation. When it comes outside, when the electron moves outside the electric field, then what is the deflection? The deflection y will be half E by m. X will be nothing but the length for which the electric field is existing, that is L by V whole square, that comes to half this is how we can find out what will be the deflection when it comes outside the electric field. The moment it comes outside the electric field, see in the diagram if I try to show, it is nothing but from O this plate to D. That is exactly what the deflection is when it comes outside. The moment it comes outside, now there is no force, hence it will start moving tangential to that path, it starts moving in a straight line. Now, what will be the deflection on the screen? What we calculated was the deflection when it emerges out of the electric field region. Now, what will be the deflection when it reaches screen? Clearly from the diagram we can say RS is the deflection on the screen, while when it comes outside the electric field, this TQ, this was the deflection Y that we have taken. Now, this being almost a straight line, what we can say is we can consider PQT as one triangle and PRS as another triangle. Similar triangles, therefore, we can take the ratio of the corresponding sides. That is what we can do here and say RS by TQ is PR by PQ. Now, RS is the deflection on the screen. Let us say that is Y. And this is TQ. TQ is our what we calculated in the previous section where we said electron moving outside electric field. This is the deflection. There we have it as Y, and this is PR by PQ. Observe what is PR. PR is, we have taken it as distance of the screen. So, we have marked it as Y is half EE by M, and we have taken it as L square by V square, and PR we have taken as capital L and by PQ. This is what we have as our expression for Y deflection on the screen. Now, our aim is to find PQ. How much will be PQ? Come to the diagram. How much will be PQ? Now, what we can do is, if we observe it, if we try to find the value of PQ. So, let us say tan theta. We can say whatever is the velocity v dash by v, this will be tan theta because we know v dash is the velocity with which it is coming out, v is the velocity with which the charge particle is released in the electric field. So, this is nothing but v dash is at by v. A is E by m, T is L by v into 1 by v. This is what we get. So, therefore, we can say tan theta is E by m into L by v square, one equation we got. One more thing we can say, tan theta is also PR by PQ. If you see the diagram, come to the diagram, tan theta is also PR and no TQ by PQ. That is what we can write tan theta as from the triangle. So, also tan theta is TQ by PQ and TQ is known to us. So, that is TQ is Y by PQ. So, now from equation 1 and equation 2, we can say E by m into L by v square, y is half E by m into L square by v square into 1 by PQ. This is what we can conclude. So, therefore, simplify it. Therefore, on simplification, E by m, this cancels out, v square cancels out, 1 L cancels out. So, PQ is equal to L by 2. So, what we can say, that the electron starts deviating from its path from midpoint of the electric field region. Pass on this equation in y. This y which is deflection on the y PR by PQ. So, this PR by PQ. Now, let us substitute. So, this y is half E by m into L square by v square. PR PR is L, capital L, and PQ is L by 2. So, on simplification, this gives us E by m into L by v square into L. That is exactly how we can find out what is the deflection on a screen which is placed at a certain distance from the electric field. Now, let us take the second case where we see that the deflection of the electron due to the magnetic field. Now, see, the magnetic field here I have represented by the cross, which means that the magnetic field is into the plane of the paper. The length on which the magnetic field is existing on the paper is small l, and the charge particle is released at O, Q. This Q is nothing but an electron with a velocity v. Observe now. As the charge particle goes inside, we know that when a charge particle is released perpendicular to the magnetic field, it starts moving in a circular path. So, it starts bending, it starts moving in a circular path. So, we can say almost this arc, this arc. So, this is OP is one tangent to the circular path, PT becomes another tangent to the circle. So, from the circle property, what we can say that OP should be equal to PT. Okay. And if we say using the circle property, this also will be same as theta. It is the angle between the similar tangents. Now, since the charged particle is moving in a circular path, so we can say BQV, BEV is mv square by r. This is known to us. So, now PT is also equal to PQ almost, we can say, because it is angle is very small. Now, this means that P is midpoint of OQ. Now, take triangle PRS. So, if I take triangle PRS, tan theta is RS upon PR, and RS is what? Y. This distance is deflection on the screen. We have already represented as capital Y, and this is L. Now, if we take the triangle OET, in the triangle OET, again tan theta is OT by EO, that is L by R. Now, see, from these two equations we can correlate and we can get the deflection that can be there on the screen when the charged particle or the electron is released in an magnetic field. Suppose that we have a situation where the electric field and the magnetic field are mutually perpendicular to each other, and if a charged particle is released there, let us say an electron is released there. Now, if the electric field and magnetic field are perpendicular to each other and the charged particle is released in a direction perpendicular to both of them, then electric field is perpendicular to magnetic field and charged particle released to perpendicular to both of them. Then it is observed that the charged particle passes undeflected, undeviated in that region, which means that the electric force magnitude wise is equal to the force because of the magnetic field. That is to say, BQV, and this is electric force is QE. So, this is BEV. So, from this we can say V is equal to E by B. What is this velocity that we are getting? How to interpret? This is the velocity, or this is the minimum velocity that the charged particle must possess, then only it can come out of that crisscross fields. If the velocity of the charged particle is less than this given E by B, then what happens is electric field and magnetic field, the one which is more dominant, the charged particle will be under that dominating force and it will start moving under the influence of that dominating field. Suppose electric field is dominant, then it will start moving under the influence of electric field. Suppose that the magnetic field is dominant, then the charged particle will start moving in a circular direction, the circular path. That is exactly how we say that this is the velocity selector. This principle is used in some places which is known as velocity selector, where all the charged particles which are having velocity greater than this velocity will be able to come out of that crisscross field, and all those charged particles which is having velocity less than this will be lost in that crisscross field. That is what we can say. This is how the charged particle has a tendency to move in a crisscross field. Now, suppose that if the two charges, this is exactly how, if both the fields are then what is the net force? That net force is called Lorentz force, you can say. That is, we can say F net. F net is vector addition of the force because of electric field and force because of magnetic field. So, what we have in this case? So, therefore, F net will be electric field means F is, here we have Q into E, and here we will have Q and V cross B. This is exactly how we can find net force acting on a charged particle when it is released in a region where electric field and magnetic field both are present. So this is the net effect on the charged particle.